Hello. Yeah, I think your marks is given today. They're giving your answer sheets. Announced. Okay, good luck. Yeah. Not increase the temperature, increase the thermostat temperature. Increase it, it's outside. Go, one of you, increase it. That's what I said, it's freezing when I came. It's not freezing? Then you should go out and change the temperature. It won't heat up by itself spontaneously. So welcome to spontaneous and unspontaneous natural tendency. Outside. How would I know, man? I'm as ignorant as you are. I'm not really good at those things, just like you. I'm equally poor. Spontaneous, not spontaneous. What's a natural tendency? What is exactly difficult, unnatural? So I think that's the 7th chapter. I'll slowly get you into 7th chapter. But before that, you did that AC air conditioning problem, so you had to find, after another air came in, the final temperature. I think your tutorial did that, right? Yes? So you had enthalpies, but you had to find the temperature of the final mixture. So in that particular problem, you can just go with Cp dt for dH. Yes? It's the same material. It's the same material. So Cp is gone. So use the tables as much as possible. I asked you independently, how can you find work in that cycle that I wrote? So I think very nicely somebody told you can use enthalpies. Yeah, you can do the enthalpies. So shall I move in to chapter 7? Sure. If I have to go into chapter 7, then you have to tell me why you need chapter 7. So far, what is it that you have done? Summarize for me. What is it that you have done so far? You sort of figured out 2 types of energy transfer. Yes? What are the 2 types of energy transfer? No, 2 types of energy transfer across the boundary. Heat and work. Can you convert them one into another? Can you? Okay. Is there any direction involved? Can you go heat to work and work to heat? Both are possible? Okay. Was there a conservation of energy? Okay. Did you worry about the magnitudes of work and magnitudes of heat? Yes. Did you worry about their conversions? Yes. What is it that you did not worry about? Yeah. Efficiency. Okay. I wonder what happened. So what is it that you, let's keep whatever he is saying, one thing in mind. He says we did not worry about efficiency. How effectively heat supplied got converted to work done. How effectively work done got converted to some heat exchange. Yes? He says we did not worry about how efficient that conversion was. Anybody wants to elaborate more than that? I think that also you did because you calculated the magnitudes. So you kind of know that you did not fully convert. correct. Because you did your arithmetic and you figured out your magnitudes, quantities you found it. So I think that also you did, but you did not write it as efficient or not efficient. That's all you did not do in any of the numericals, correct? But you did convert it. You wrote the numbers. Independently you wrote the numbers. If I heat a material, how much work it takes. I think you did all that. But you just did not write it explicitly. So little bit think, what is it that you have to also consider? What you have done so far is you have told Q can become W, W can become Q, this much of W is this much Q, this much Q, this much W. Net heat transfer, net work transfer, life is good, conservation of energy, everybody is happy, go home. Anything else that needs to be thought about? Anything else? Thermodynamics is notorious in hiding the rate. That's the whole point in thermodynamics. In equilibrium thermodynamics is notorious in not even talking about kinetics. Thermodynamics hides kinetics. Anywhere do you hear how much time it takes in thermodynamics, equilibrium thermodynamics? So what they do in your curriculum is, there will be a thermodynamics and then there will be a kinetics course. So they split it. So little bit the time thing you can let it go for now. It's a thermodynamics course. And more specifically it's an equilibrium thermodynamics course. What else do you need to think about? It should come from you only. Then I will start chapter 7. You said efficiency in a way, but that has so many layers in it. So we are talking about conversions of two types of energy transfer. But what else do you need to consider? So heat, pardon? Louder. Spontaneity. What could that be? You can just tell me what that English Webster meaning is. Spontaneity. What is spontaneity? If there's a joke, you laugh spontaneously. What does it mean? Huh? Say that again. I think you're pretty close. One more time. No need of any work. Welcome to chapter 7. No need of any work. So no need of any work is spontaneous means, is it natural of not doing work or is it unnatural? Huh? Natural. All of you getting oriented and walking in the corridor and coming and sitting in one confined room, is this natural? Or all of you dispersed and doing your own activities wherever you feel like, however you feel like is natural? So you know what natural is. You want to disperse, the more disperse. So when you do dispersion, do you go from small to big or from big to small? So can I write it like this? Which is natural? A. For B to happen, it will happen, it won't happen spontaneously. What do you need to do? You need to do a lot of work. Localizing something and putting it in order and getting it oriented and giving it a push and giving it a thrust and giving it a scalar, vector, tensor, very difficult. You have to do a lot of work. The other way around, give me an example. If you say A is natural, I already gave your example of coming to class. So this is unnatural. Basically, this is an unnatural environment, if you really think about it. You agree? I agree too. So, if this is unnatural, how do I make it natural? I'll give you 200,000 points right now. So this is unnatural. How do I make this natural? Other than opening the door and telling run away. Other than those kind of things. You still are going to be seated here in an unnatural manner, but how do I make it natural? You can lose the phone, man. Haven't I already told one time in the class? Go read the videos. Go see the videos. You're making me do work, which I actually don't like. Example of dispersion. Mind wants to wander, mind wants to digress, mind wants to do million things. Mind does not like to orient. Mind's a monkey. That's the natural thing, so don't fight against it. Mind is a monkey. Try to tame it, but you should also acknowledge that it's a monkey. It's a monkey that can be tamed every once in a while, not always. So you are in a very unnatural situation. How do you make this natural? For what? To become more unnatural, so that you orient towards the reward. That is, I'm doing work. Good start, very good start. It's the other way around. You made me do more work. Made you more oriented towards one particular goal, and that becomes more and more unnatural. All of you are getting localized and focused on one particular thing, not a natural thing. Firstly, you're in unnatural situation, so if I put reward, it becomes more unnatural. So how do I make it natural? So a little bit you can elaborate on it, which I've already told in the class many times. It's not good if I talk from this side. What is good if you talk randomly from that side? Then it becomes a slightly natural process. If I keep on talking from this side, it's an oriented process. If you randomly shoot off whatever you feel like from that side, then slowly it begins to become natural. Because you can say some irrelevant thing. You can digress and you can say something very irrelevant. And that makes it more natural. You can disperse your mind. But if I keep talking from this side, your dispersion will start to decrease further. So you can still convert an unnatural into a natural. So what do you need? You need more interaction, not from my side. From which side? Okay. So give me another example. Now give me an example. You coming to class is my example. Give me a nice example of spontaneity where dispersion is natural in that particular direction, but the reverse of that, close to impossible. Think and give me an example. Again, if you want, I'll give you another example of mine. I can disperse both energy and matter, both. So I throw some sugar and water. So there is spontaneous mixing. Yes, I don't actually need to do any of that thing. It will go into molecular dispersions by itself and it will intermix really well. Obviously there is some kinetics involved for it and that will happen. Is that spontaneous? So both energy as well as matter got dispersed. Did it go from small to big? Sugar went from a small local cluster to a big area, big volume of dispersion. Yes? So mixing is a spontaneous process. But then you have also seen demixing, clustering, correct? Demixing. So then what happened to demixing? Demixing is, so it cannot come back to sugar. Once you throw it in water, can it spontaneously again come back? Not spontaneous. But can you make it happen? How? Huh? So I threw sugar in water. Naturally, it spontaneously mixed out. Great. Is the reverse possible? So the sugar dispersed, some of its energy got transferred to water. Water became more mobile, more random. For the reverse to happen, all that, if I heat, what happens? So let me heat. So what you are saying is, let me do some heat. No vaporizing. Yeah, now that will all become different business. No vaporizing, but I'll allow you to heat. If you heat, now you sort of supplied energy to water. Now did that water molecules which gained heat, does it make their random motion to get ordered and oriented and make sugar into a crystal? Does that happen? Even if water gained the energy, it won't orient from a big volume and localize all the energy into sugar and make sugar into back again into a crystal. Not going to happen. Very impossible. Yes? Not going to happen. Give me your example. I'm still waiting for your example. This is what reversibility is. So direction is something that you need to worry about. So welcome to second law of thermodynamics. First law did not worry about spontaneity, direction. It just said you can exchange Q to W and W to Q. You can have net Q and you can have net W. Do we care about directions? No. So suddenly after that, do human beings remain quiet? No, their entropy keeps going, right? Their dispersion keeps going. And somebody thought what is natural and what is unnatural. So what is natural is only if dispersion happens. The signpost is something is spontaneously possible if the arrow depicts or directs towards more dispersion. Otherwise, it is not spontaneous. You have to input something unnaturally as work or heat to make that happen. Yes? Yes? But I need still an example for you. Pardon? Okay, helium balloon. What about it? Okay, it will go up. So why it goes up? What is it dispersing there? What is balloon transferring? To who it's transferring? At the end of the day, it has to disperse. Either it has to disperse in the system or it has to disperse to something around it. So once again, I'll come to helium. Even if you unnaturally make that sugar demix and become sugar again, what will be given out? Because they were all happy and nicely moving sugar. you made them unnaturally come together and demeth. So did their translational energy decrease or increase? Decrease. So what comes out as a consequence? Heat comes out. Who receives the heat? So what happens to the thermal motions of water? Increases. Still, at the end of the day, whether you do it naturally or unnaturally, the entropy or the dispersion of the overall system and the surroundings should increase, or it should remain the same. It can never decrease. Clear? So that's why I just told this as helium now, because that is possible if it is giving out heat, and if the air molecules are all happily getting dispersed, then that's possible. Then that's spontaneous process. The unnatural thing of that is to get that heat from all the surrounding air and put it back to helium and make the helium come down. That's impossible. Won't happen. Won't happen. Another example. Opening the gates of a dam. Gush. Okay. So what did you do? Work or heat there? Its mass is getting dispersed. Energy is also getting dispersed. That's natural. Opening a Coke bottle. Okay. I think it's very spontaneous, yes? The other way around, to compress it and shove it into one bottle, difficult. You have to do a lot of work. And when you do that work, there is heat that is being given out to the surroundings. Got it? Otherwise, that process also will not happen. Eventually, your dispersion should happen to your system, as in your Coke, the gas in your Coca-Cola, or the surrounding should get the dispersion. Either one of them should get the dispersion, and the overall dispersion should increase or remain constant. If it doesn't happen, if both of them like become oriented, and not going to happen. Yeah, there is no process that it's going to be like this. So go back to your learning example. Your heat supply is your book. So there are some concepts in the book. So you like to do some work and you get a little bit oriented because heat is being given. But that is not very natural, but you still manage. What is a more natural thing when you are doing that learning? Be honest and tell me. You take a book, there is heat there, there is orientation, concepts are there, words are there, paragraphs are there, sentences are there. Then what happens? There is a conflict between natural tendency and unnatural. So what happens? What is the natural thing that happens as soon as you... Come on. Everybody knows this. Everybody does this. Everybody has experienced it. What happens as soon as you open book and start looking at some sentences? Huh? You feel sleepy. Okay. You feel dreamy actually. So what all things happen? Some digression begins to happen. Some ideas begin to kick in. Tangents, confusions, unconfusions, irrelevant things, future ideas. All very, very natural. Yes? So if that becomes a lot, what happens to your, how much work that is actually required, as in you have to orient to what is put in the book. What happens to that? Decreases. So has anybody achieved a very classical 100% book? Without any digression, without any dispersion, without any distraction, without any going around, roaming around in the mind? Anybody? like 100%. Give, go for it. Go getters. Anyone? It's possible, but it's very, very unnatural. It's very, very unnatural. When an input is given, if that input is correctly used for an oriented act, as in work, it's very, very unnatural if all of that. There is going to be a lot of dispersion and wastage, where you are going to go and unload a lot of your whatever you have received into some other place. Yeah? And you are going to discard it. That is going to be natural. When you discard it, who takes it? The surroundings takes it. Your friends take it. The entropy of your friends will increase. And that is cool. That will happen. Yes? Because you cannot orient, you digress, and you go and dump it on your surroundings. And who are your surroundings? Your buddies. Do they get oriented? No. They disperse it some more and go dump it on someone else. It's a good process. It's a natural process. Very difficult to do work, very difficult to orient. So does that mean that we don't do work in our lives? So I can cop out and say orientation is not natural, and so just quietly just sit down. Is it possible? Is it possible in life to orient? Huh? Yes or no? Really? Is not convinced. Is it possible to orient? Is it? But you have to acknowledge what? Proud of? Also you have to acknowledge what else? Most important. Lot of effort has to be put, lot of orientation has to happen, lot of localization has to happen, lot of unification has to happen, but you also have to acknowledge what? Exactly. If you acknowledge that, then you will maintain your sanity when you try to do work. But if you don't acknowledge that and think of a very efficient system, then your brain will hurt. Yeah? So acknowledge the natural tendency and try to do some work every once in a while. How about that? Does it make sense? Yes? Acknowledge the digressions and the tangents and the dispersions and the wastage and the discarding, but try to do work every once in a while. Knowing that that is natural and this is unnatural. Another example. I have a ball. I drop it on the floor. Spontaneously, does it bounce off? Is the energy so it bounces off. Does it bounce to the same height infinitely? No. So dampening is happening. The energy is getting dampened where? From the ball to ground. So it can come out as heat or sound. So let's say it's heat. Let's leave out sound for the time being. So who receives that heat? The floor. So the thermal motion of the floor will increase and it will disperse really well. Life is good. This is spontaneous, happens. Now let's keep the ball on the floor and let's heat up, somehow you have heated up the floor. So there is thermal motion in the floor molecules. Will they all now come to a local place and orient and make the ball go? Not gonna happen. So just be careful before you tell what is a reversible thing and what is a non-reversible thing. So solid to liquid to gas and gas expanding, is that natural? The other way around is you have to do work. Exactly the other way around, you have to do work. It's doable, but you have to do work. You have to pay money and you have to do work. Clear? That's all I came here, to introduce you to dispersion. So what is this dispersion called in a fancy way? Huh? Randomness. Okay, you like the word randomness. What else people use? Something. They also say disorder. Okay, disorder. Thermodynamically, entropy. So procedure or a process or anything is spontaneous if the entropy of either the system or the surroundings increases substantially, wherein the total entropy of the universe will increase. So I'm just going to leave it as a very simple word, dispersion. So now I think one time I asked you in one of the classes, if you bombard a material with energy, what are the few things that will happen? I think one of the things that came about was distribution or dispersion. That is your heat capacity. Yes? Get it? That is what capacity is. What you are doing is you are taking that energy and dispersing it. You are not doing work, you are not conducting it, you are not reflecting it, you are not scattering it, you are not using it to tear the material, you are not exploding, there is no chemical reaction happening. What it's doing is it's simply getting dispersed in your system. That is heat capacity. So do you want a battery which should have a high electrical heat capacity or no? A battery should have high capacity or no? Battery. Nobel Prize just got awarded for lithium-ion batteries. Everybody wake up, welcome to material science. A battery should have high capacity or low capacity? Huh? So I wonder how that will be possible. Should it be highly dispersed or less dispersed? I just gave you an example of heat capacity. A heat will be capacitated or held if there is more dispersion in the material or less dispersion in the material. More dispersion. Heat is heavily dispersed like a bottomless pit. Got it? If you have that, heat will nicely get dispersed. So do you want a battery to have a high capacity or no? Firstly, yes or no? Yes. So then should it have high dispersion of electrical energy or less dispersion? Obviously. So you have to make a material that can disperse electrical energy really, really well, so that you can store it. You should not say absorption. There is no absorption. Absorption means it takes that energy and gets excited. Got it? It gets excited. There is no excitement happening in a battery. It just takes the energy and it just distributes it, because it can move. It can move, it will distribute. So you need something that can move. Yes? Now, does significantly if I put sugar in water, does the energy change? No. The internal energy won't change significantly. What will happen is the dispersion will change significantly. Get it? The dispersion will change significantly. The internal energy will not change very significantly. You just gave it more configurations and more probabilities and more combinations. So it will combine more and it will move more. So when you keep on supplying energy, it will hold it more, because it can move more, because it can have more combinations. So what you talk as randomness, disorder is combinations. You can have more combinations. 52 pack of cards. How do I make more combinations? Get another pack and mix it. What happened? Entropy increased or decreased? Tremendously it increases. It just shoots up like exponentially. Yes? Every once in a while play a little bit of cards. You will get a good concept of combinations. How to make combinations. So if you put multiple things, your combinations will increase. Increase. So that's what the battery is about. So high heat capacity, high electrical capacity, and high mechanical capacity. They all go hand in hand. Does a pillow and a mattress have a high mechanical capacity? A pillow and your mattress. Does it have the ability to distribute and disperse energy that you are supplying from your body weight? Sure. If it did not have, you would have felt it. How you would have felt it? No, you would have fallen off from the bed. It will reject you and throw you out. Yes. It will say, I don't want this energy, and reflect it back, and you will be on the floor. Correct? I hope you understand. It's simple common sense. If it doesn't distribute, it has to reflect and reject. Correct? What is rejection? You are on the floor. That's all. So how is that energy getting dispersed in the mattress? Mattress is a big industry. Battery is a big industry. High heat capacity materials is a big industry. So all this energy capacity materials is a big thrust area. It's a big industry today, whether it's electrical, thermal, or mechanical. Everybody wants a high dispersing material to be done and given to them in any product. So you feel like you can keep using it forever. And it gives you a lot of usage. As it should, it does, yes? But for that it has to hold. How does it hold? How does a mattress hold your body weight? How does it disperse your body weight forces? It stores. How? It disperses. It distributes. It does not store in one location, otherwise it will tear there. There is no localization, there is a dispersion, correct? The mattress, your local body force is dispersed. How is it dispersed? I'm just asking about a real product that you just slept on and came. Okay, springs will do what? They get activated. They get activated. No, they don't get activated. They do get activated. As soon as you sleep on it, the springs will get activated. It's just like the ball falling on the floor. What else happens? It's not just a spring, because if it were a spring, then it's very rigid. You will find it too elasticy. You don't like it. You also like little compliance. It has to change shape. Memory mattresses, memory foams. How does memory foam happen? It has to change shape. How does shape change happen? Something has to move there inside. What is moving inside your mattress? Foam is not moving. Foam is foam because it has something in it. That's why you call foam as foam. Louder. Air. Yes, air is moving. Who is dispersing there? Air. What is it dispersing through? Cells. The cells can be independent cells, or those cells can be connected to each other in your mattress. So you have foam. That is what a foam is. Foam is where you have pockets inside. What is the pocket filled with? Air. And that air has to move. If the air moves, you will disperse your body weight. Good. Get a good feel for dispersion. Something has to move. That is the essence of dispersion. Something has to move. Something has to configure. Something has to get activated. So if you have a material that can activate a lot, that can move a lot, that can configure a lot, that can combine a lot, then you have a very good energy holding material. The same thing opposite of that is rigid, frozen, not very highly activated, immobile. What happens? You will get blocked, or it will all come out. It will get reflected. It cannot get excited anymore. Clear? Is the ball example sufficient? Now use the heat engine example, just like you're studying. What do you supply for heat engine? The word itself says heat engine. What are you supplying? To do what? Engine work. What is engine work? Again, work has to involve some kind of movement. It has to rotate something or it has to push something. So what do you do to supply heat? Either you supply electrically or you create some exothermic reaction, combustion. So you supply heat. What will that heat do? It will go and give you some work. I think I already went through this. I'll write the diagram again if I have time. It will do work. What will happen to that material after it does work? It cools off. But still, it will also have some heat and it will go and discard it somewhere, because it's not 100% conversion of whatever heat you supplied to the work, because our friend the material will get thermally activated and will become more random. Just like your mind when you're studying. What happens? He cannot orient completely. So some of the heat has to go to the dump and get discarded. Yes? So when it's discarding, slowly it begins to phase change. It was highly activated, it starts to become less activated. It starts to become condensed. It becomes condensed because now it's not more random anymore, correct? It's discarding the heat. Is that a good thing that it's becoming condensed? Yes, because the next step is you put it through a compressor. So it's already getting condensed, so it's easy for you to compress it. And then you heat it back again, then you get the work. Heater, work, condenser, compressor. Right? That's your heat engine. Supply, so from now on, wherever you supply the heat, guys, call it as supplying heat at the hot junction or at the hot location. So don't simply write Q like how we were writing in the previous chapters. You write QH. It's the hot junction. QH. You got heat and your material became highly agitated. So can it become like a water becoming vapor? So it can be a boiler, evaporator. So what device is this? Evaporator or a boiler. Then what do I get here? Work. Work. But all of that agitation will not go into oriented work, correct? It still will continue to remain agitated, and that has to come out here at the cold location. So what notation shall we use? Hot. Your book uses L, low temperature. High temperature, low temperature. That is where the heat is being dumped. It's getting discarded. Yes? And what device is that? Sink or a condenser. A condenser. So first one is the evaporator. Then you got the work done, a moving work turbine. Then you came down and discarded the remaining heat. Sink, a cold sink. A low temperature junction, a low temperature location or a low temperature junction. Where you receive heat is from a hot temperature junction or a hot temperature location. Where you dump the heat will be a low temperature location. And then you condense. What happened next? Compressor, pump, compressor, and then back again. So in the compressor, obviously work is being done on your material. So you can just put a W there. So is there a net work done and a net heat done? Is there a net heat done? Yeah, there is a net heat and there is a net work. and your engine goes round and round and round. Clear? Pretty simple. So a little bit, the only new thing is previously we used to simply write heat being received and heat being given out. So here you have to say where you are receiving the heat. You are receiving heat at a hot junction, QH. Where are you discarding the heat? At a cold junction or a cold location, QL. Now can you nicely write what is the efficiency of this engine? Output divided by input. So I already told you it is heat engine. What are you supplying? Heat. So what is the denominator? Input. Write it, man. What's the book closed for? Efficiency. Output by input. So what are you supplying as the input? Louder. QH. What are you getting out of it? Work. Work. So W by QH, correct? W by QH. So can you write the work done in terms of heat? How? QH minus QL. Very good. Because whatever QH is supplied is equal to how much QL is rejected plus the work done. Can you write that also, arithmetic? Quickly, write it. QH is equal to QL plus W. W is equal to QH minus QL. So now you got your efficiency as QH minus QL divided by QH. Now how do you get a 100% efficient system? Look at your equation and tell me. QL is 0. Is that possible? Not possible. That's the Kelvin statement. The Kelvin statement says that it is improbable to convert all the heat that's being supplied to work without any rejection of heat in the cold junction. Get it? That's the Kelvin statement. That's one of the definitions of second law of thermodynamics. So what is it exactly telling? That the entropy of the universe should still increase. So that rejection QL is how the entropy of the universe will increase, because that heat is being supplied to the system or to the surroundings? Surroundings. Only then that process is possible. Got it? So there are many ways people talk about second law, but eventually it will come down to dispersion should happen. If dispersion does not happen, the process is not going to happen spontaneously. So I think that's why I came here, just to start you off on heat engine. Next class I will slowly get into heat pump and refrigeration. I think then you're set for some numerical. Good? Take